Well, getting a bit worried because as I said, there are three components to my part of the talk. Okay, first component on stability margin and sensitivity function. So there is definitely one question in the sense. Okay, second component on PID and hole placement with polynomial. Okay, so for these two, they have been given some exercise questions and tutorials to go back to work on. Alright? And there are lots of past exam questions that we'll go through in the revision lecture. And the last component which we're going to do now is space. Okay? So for the revision lectures, we'll probably go through each of the exam questions and the whole project to be small. But in order to make it useful, alright, at least before the lectures, please go through some of the exercises that were given to you so you know what or at least print them out and bring them to lecture. Alright, so you know what the steps to follow. Otherwise, it's quite a waste of time. Okay? What I'm going to tell you next is there are some past exam questions that are worked on below. So, as a set of sample of exam question you can try now, if you like, the oval, question 1, 5, and 6. Alright, then for 2012, 2, 5, and 6. And subsequently, it's always 2, 5, and 6. Alright, so, okay, from 2013 is on 2, 5, and 6, but 6 is on 6 days. And then, 2014 is 2, 5, and 6, but 5 is on 6 weeks. Okay? Alright? Question 2 is compulsory, so it's always compulsory. Okay? So you'll be very concerned, especially if question 2 is compulsory, because you're not sure if this space is going to come out, or will it be stability margins and sensitivity functions and some parts of PID controller as well. Alright? So for the first two components, stability margins and sensitivity functions, I told you, they need to memorize. Alright, PID controllers, there's some memorization required. Design with the Diophantine equation and hole placement or normal is something in practice. Okay, but for the past 2 years, there's definitely not question this week. Okay? Alright, and there may be a possibility that one of the questions is combination. So, like question 5, it could be state space, and question 6 is not wholly polynomial or wholly discrete. So half the question is polynomial, the other half the question is discrete. Okay, so don't pick and choose. Alright? And question 2 may be half polynomial, half discrete. Okay? So just take note, if you want to practice, you can start now. Alright, some questions are available. We'll go through them in the revision lecture. Okay, so a very quick recap of where we left off the last time. We're looking at basic mathematics. Alright, remember without state space control. Okay, so without state space control, in state space we say that the system is always x dot equals x plus bu, y is cx plus du. Okay, so an example of A, B, and C for a second order system is something like that. The transfer function is always this, CSI minus A equals B plus D. So in one of the past year exam, you were asked to write the transfer function, GS. Okay, so we have gone through this before. What you take note is, end of day, with this transfer function, you realize that the core of the system is identical to the eigenvalue of A. Okay, so we've gone through this. And then with state space feedback control. Alright, in one of the past year exam question, you're asked to draw what's the concept of state feedback in block diagrams, so this is what I draw. Okay, once again, X are states. Okay, so this ought to be a vector, otherwise concept will be charted. Okay, the main idea with this state feedback control is control law, U is minus K of X, minus K times X. So we put that in there. End of the day, the transfer function is C Si minus, in bracket A minus Bk. Okay, reverse. Alright? And the closed loop holds with the determinant of Si minus A minus B. Okay, so these are the important concepts that we have taught last week. Okay? Now, so if you think about it, we said that, for instance, if you have a robotic arm, okay, the states can be like angle, yes, the rate of change of angle, and the acceleration. Is that unique? Are those the only states that we can have?
Okay.
Any guesses? Yes or no? Huh? No. Okay, so I can have rate of change first, and then the angle, and then acceleration. Or I can have position of the robot, followed by the angle, and the velocity. Alright, so states are not unique. Okay? So you have any states. Alright? So this is where we talk about similarity transformation. Okay, the definition of the state is not unique. Alright? So we say that states can be linearly transformed. Okay? From X, which is one set of states, to X bar, another set of states. Whereby they are related. Okay, through a transformation matrix, T inverse. Okay, but what's more important to know is that T has to be non-singular. Okay, what's the meaning of non-singular? The rows have to be linearly independent. Okay, so if this is a second order system, T, the rank of T must be 2. Okay? So from my experience with the students last year, they are not quite sure what's the meaning of non-singular. Alright? But before we go into that, okay, let me just illustrate to you what happens when you have such a transformation. Okay? So what we are saying is that we can actually define a state xt, alright, and another set of states x bar in this manner. Okay? Such an x bar is T inverse xt. Alright? So this is no longer a scalar, it's a vector, because states are vectors. Alright, so we move this on the other side, section and inverse. Okay? So originally when you have the states as xt, the system was x dot equals to ax plus bu. The y equals to cx plus bu. Yeah? Now you're trying to use another set of states, x bar. So we will expect that x bar will be defined as this, right? X bar dot equals to ax bar, a bar x bar plus b bar u is u. And then y is c bar x bar plus b bar u, because we're talking about same input. Okay? And then x bar 0, t inverse of x 0. Okay? Alright, the next question is how is A and A bar, B and B bar, C and C bar, how they related? Alright? Okay, so from 1, alright, what you do is multiply T on the left and the right hand side. Okay? Alright? So from 2, not from 1. From 2. Okay? So you multiply T on the left and right hand side. So T x bar dot, okay, would then be E. Okay. Yeah. All right. Okay. And then Y. Leave it as it is for time being. Okay, and then from 1, what you can do is, this is x dot, right? Okay, and you know that xt is t x bar. Yes? So what is x dot? Differentiate the left and the right hand side. Okay? So you have t x bar dot is A. Okay, x is now t x bar plus du. Okay, this from 1. So x is t x bar. X dot is t x bar dot equals to A t x bar plus du. Okay? You get rid of this t, so you have t inverse t inverse at plus t inverse u. Okay, t inverse t is your identity matrix I. Star dot equals to, so that this is A bar x bar plus B bar U. Okay, I times x bar dot is just x bar dot, right? So we can just remove this. Yeah. So if you compare this, 3 to 2. It's very obvious that A bar is just t inverse AT, and B bar is t inverse B. Okay? Yeah? 3 is the same as 2, right? Yes? So it's very obvious that A bar is t inverse AT and B bar is t inverse B. Any questions? Okay, you can continue for the output. Okay, so output is y equals to c. Okay, what is x? X is t x bar plus du. So this is actually c bar x bar plus b bar u. Okay. So C bar is just CT and B bar is just B. Okay, so when you actually transform one state xt into another state x bar through a similarity transformation matrix T. Okay? All your other matrices and vectors will be transformed. So A, B, C, D will be transformed to A bar, B bar, C bar, and D bar. And how are they related? A bar is actually T inverse of AT, B bar is T inverse of B, C bar is CT, and D bar is C. Any questions? Okay, so if there are no questions, alright, the result is exactly what you see in the slide, like this. Alright, this is the result, and this is the derivation. Okay, because all of you actually learn at different speeds. Alright, so as I said, some of you prefer to copy, some of you prefer to just understand. Alright, so for those of you who feel that you cannot follow, anytime when you feel that you cannot follow, either come to me during the break or write me an email and you come to my office. Okay? So the only thing you have to be sure is do not be shy to ask if you're not sure. Alright, so let's move on. So you clear about the derivation. Yes. So this is what I see in the next slide. That if you were to do this transformation, what you end up with is this. So instead of x equals to a, x plus bu, you end up x bar or equals a bar x bar plus b bar u. And a bar is t inverse at, b bar is t inverse b. Okay? C bar is ct and d bar is u. Alright. So we say that actually, essentially, even though you have changed the another set of states, alright, but the characteristics between the input and output are not changed. Okay, but the internal states are now different. Alright? If that is the case, what will happen to the transfer function? Okay, so if you use this A bar, B bar, C bar, and D bar, then we have said before, the closed loop or the open loop transfer function is like always C bar Si minus C Si minus A inverse BU. Okay? So now that you have done the singularity transformation, instead of C, it becomes C bar, A plus A bar, B plus B. Okay? And the initial condition x0 plus x bar 0. And we have said to you that C bar is actually CT, A bar is T inverse AT, B bar is T inverse B, okay, and x bar 0 is T inverse x 0. So if we put that in, we'll form the same transfer function. Okay, with the space as xt, so it's C S minus A inverse BU plus x 0. So the transfer function is no different. Okay, with the change in space, the transfer function is the same. Alright? So we see that different choices of state variables can have different internal descriptions of states. Okay, but the transfer function is always the same. But the criteria, at the end of the day, if there is singularity transformation and it relates from x to x bar, must be non-singular. Okay? So what's the meaning of non-singular? Okay, if T is 1001, is this singular or non-singular? Then this will be non-singular because the rows are linearly independent. Okay? But what if T is 1020? Is this non-singular? Or singular? Singular, right? Because you can describe the second row by the first row. Understand it? T. T, if it's 1020, alright, you can see that row 2 is just 2 times row 1. Yes? Right? So the states will not be independent. Okay, so this is the meaning of non-singularity. The rank of 1001 it has a rank of 2. Okay, the rank of 1020 has a rank of 1, which is lesser than ordinal order. Okay, so this is singular, and what is non-singular. Alright? Okay? So if you understand similarity transformation, we say that we can actually describe, okay, we can describe a state space model in many different forms. Alright? So similarity transformation T can be used to bring a system to a special form, which are called canonical forms. Okay? And the transformation of a matrix of eigenvectors result in a certain canonical form, which has eigenvalues and regular values in the split matrix. So, a race of S who understands eigenvectors and eigenvalues. Okay? Alright, so we need to revise some basic math here. Alright, for other canonical forms, just take note that we have so-called controller canonical form and observer canonical form, and they can be related to similarity transformations. Okay, so some basic math revision. Okay, so we have just gone through this. That it can be any, alright, the states from X to X bar through a similarity transformation T. Basically, you can identify and write down the same state space equation. So that A is now T, A bar is now T inverse A T, B bar is D inverse B, C bar is C T, and D bar is D. Alright? So there's no need to argue, there's no need to fight. It's okay if you want to define your states as x1, x2, x3, and another person might define my states as x2, x1, x3. It's fine. Okay? Alright? Criteria is T must be non-singular. Okay, in math terms, we call it full row rank. Alright, so if it's a 2 by 2 matrix, the rank must be 2. Meaning the first row and the second row must be linearly independent. Okay, they are not dependent on each other. So some examples. 1001 is full row rank. It's not so meaningful because if T is 1001, X bar is T of X, right? So X T X is the same as X bar. They're exactly the same. Okay, so not so meaningful. Okay, so some examples of T will be 1101. So this is still full row rank because you cannot use row 2 to define row 1. Okay, they are still linearly independent, or it can be 0, 1, 1, 2. Okay, and etc. Okay, what's the minimal definition of a singular example, a singular matrix like 0, 1, 0, 1? That's silly, right? Because row 1 and row 2 are exactly identical, or 1, 1, 2. Okay? Alright? So this is something that we've already gone through. I just want to point out that, for instance, this is an example of ABCD, and we end up with a closed transfer function. Alright? Just note that if you are asked about closed loop polynomial, meaning the characteristic equation is always the denominator, x squared minus 1. And this denominator happens to be the determinant of Si minus A, the open loop. And the determinant of Si minus A are the same as the eigenvalues of A. Okay? And these are also the poles in the closed system, right? Okay, and similarly, under state feedback control, if you work out the transfer function, ys will be c si minus acl, where acl is b minus a minus bk. Alright, the closed loop poles will be eigenvalues of a minus bk. Alright? And you can ask about the closed loop polynomial, The closing polynomial will be the determinant of Si minus A minus BK. Okay? Which are the eigenvalues of A minus BK? And they are also the poles of the closed system. If you solve for the determinant of Si minus A minus BK. Okay? So this is what we learn about eigenvalues. So eigenvalues of A, okay, are the poles. Yes? Under state feedback control, eigenvalues of A minus BK are the poles of the closed system. Okay? What are eigenvectors? You don't have to copy this, just understand. Okay, practice basic math. Okay? So, in mathematics, alright, we say that, for instance, if A is this, 0, 1, 0, 0, 2, 0, 0, 0, 3. Okay, you see that it's a 3 by 3 matrix. Yes? So in a 3 by 3 matrix, you have 3 eigenvalues. That's 3 eigenvectors. Okay? So eigenvalues will be like lambda 1, lambda 2, lambda 3. And eigenvectors will be v1, v2, v3. Alright? And how is this defined? This is a linear equation. Huh? So if you have A times the eigenvector B, meaning anyone, v1, v2, and v3, this will be equal to the eigenvalue, the corresponding eigenvalue lambda as V. So if you have A V1, okay, A V1 will give you lambda 1 V1. A V2 will give you lambda 2 V2. And A V3 will give you lambda 3 V3. Okay? In some of the modules you have learned that for the matrix, okay, the direction times the direction of the matrix will give you the corresponding magnitude, which is eigenvalue in that following direction. Alright? So just illustrate to you, let's say for instance, alright, you know that from here, okay, one eigenvector will be 1, 0, 1. Alright? With a corresponding eigenvalue of 0. Okay, another eigenvector will be 0, 0, 1. So because look at the last column, let's see 0, 0, 1, we look at the last row, that's 0, 0, 3. So 0, 0, 3 is 3 times 0, 0, 1. Yeah? So if A dot 0, 0, 1, meaning if you find, okay, the direction of 0, 0, 1, A, okay, so if you do this, you see the direction of 0, 0, 3, that means the eigenvalue is 3 in this direction of the eigenvector 0, 0, 1. Alright? Another eigenvector 1, 2, 0, so we do A dot product 1, 2, 0. You end up with 2, 4, 0, which is 2 dot of 1, 2, 0. So you know that eigenvalue, the magnitude in that direction is 2 in the direction of 1, 2, 0. Okay, so the eigenvalues are 0, 2, and 3 with corresponding eigenvectors 1, 0, 1, 0, 0, 1, and 1, 2. Okay? So this is actually covered in A-level mathematics. I don't know, I think it might be some components of the covered as well, either in the polytechnic or in applied mathematics. I'm not sure. Okay? Alright? Okay? So some questions that students may have is, how do I know what are my eigenvectors? Because I need to know my eigenvectors, right? So I can identify my eigenvectors. Alright? You can tell by looking at the columns easily. First one column is 1, 2, 0, so 1, 2, 0 can be 1. Another column is 0, 0, 3. So it is 0, 0, 1 can be an eigenvector. Okay, what column is at least 0, so it will be 4 over 5. Okay, this is usually how we go about doing it. In this module, I am required to compute eigenvalue and eigenvectors. Okay, so that's not required, but I'm just explaining to you so you understand. Alright, now one thing that you really have to know how to do, like I said before, you have to know how to compute poles, how to compute pole location if you are given a matrix A. Okay, so without state feedback control, if you are given a matrix A, as I said, you need to know how to compute what the determinant of Si minus A equals to 0, because that will give you the pole location. Alright? So take for instance, if we have a 3 by 3 matrix. Okay, this is a warning. Don't assume that the maximum order we can go to is 2 by 2. Okay, we may have questions on 3 by 3. And then that's why you don't know how to compute a determinant, you cannot compute a closed group. Alright? So if you have a 3 by 3 matrix, okay, so this is how you do the computation. So determinant of Si minus A. Okay, a 3 by 3 identity matrix with 1, 0, 0, 0, 1, 0, 0, 0, 1. Alright? A, example 0, 1, 0, 0, 2, 0, 0, 0, 3 goes to 0. So S of I is just S 0, 0, 0, S 0, 0, 0, S. Yeah? Minus this, you have S minus 1, 0, 0, S minus 2, 0, 0, 0, S minus 3. Alright, how to compute the determinant? Okay, what you do is you keep the first corner S, they give you a positive sign, so positive S. Okay? And then you compute the adjoint. So you cover this, and you cover this. Okay, and what you have left is S minus 2, 0, 0, and S minus 3. Okay? Then you compute S minus 2 times S minus 3 minus 0 times 0. Okay, so you have plus S times S minus 2 times S minus 3 minus 0. Then we move on to the second column. Okay, minus 1. So the second column you put in a minus sign, so minus of minus 1. Okay, and what you have left for the extra is 0, 0, 0 and S minus 3. Okay, so 0 times S minus 3 is 0, minus 0 times 0. Okay, then move on to the third column. 0, the positive sign, so plus 0. Cover this and this. And you are left with 0, S minus 2, 0 and 0. Okay, so plus 0, 0 times 0 is 0, minus 0 times S minus 2 is 0. And you equate the entire determinant to 0. So you end up with this. And it's very obvious that S is 0, 2, and 3. Okay? So this is also one way for you to identify your eigen values. Okay? Alright? So now do you understand eigenvalues, eigenvectors, eigenvectors? Okay, so let's take a quick 5 minutes break. We'll come back at 3.
那个
Okay.